kinetic energy of a moving body. Suppose this is an object. We are exerting a force F constantly over it. Now this object, the force we are exerting continuously, okay? Therefore, this made a displacement. So until it reaches here, this force should continue. This is called constant force. And here, since force continues exerting, this body will gain a uniform acceleration. Initial velocity U, final velocity V, and displacement is S. These are the data you must know. So here, we know F is equal to, W is equal to, work done, W is equal to Fs cos theta. Okay, then theta is equal to 0, cos 0 is equal to 1, and W is equal to Fs. Here, F is equal to ma, and V squared is equal to U square plus 2as. Then W is equal to, F is equal to ma. From here, one more step. Here, V squared minus U squared is equal to 2as. S is equal to V squared minus U squared by 2a. Then substitute the values of F and S in the equation of first. W is equal to F is ma, S is equal to V squared minus U squared by 2a. Okay, now we can write.
Sir, can you please repeat?
From the beginning?
Oh, from this part.
Oh, okay. So F is already ma, S is given here, right? Substituting
Yes.
this value of F and S in this equation.
Okay.
Then W is equal to F is ma, S is V squared minus U squared by 2a. Okay. Then here, what's the mistake? Yeah. Some mistake we are making. 1 minute. Cancelled here. Then W is equal to half mv squared minus half mu squared. This work done producing a change in kinetic energy, isn't it?
Yes.
So work done is equal to change in kinetic energy. If U is equal to 0, initially object at rest, then W is equal to half mv squared. This work is converting into kinetic energy, that is Ek is equal to half
mv square.
This is the formula for work. Okay, write down. First draw diagram. Only diagram you draw, then I'll give the note.
So what is the heading?
What is the
Heading.
kinetic energy of a body? Kinetic energy of a moving body. Kinetic energy of a moving body. Let m is the mass of a body. Let m is the mass of the body. Let m is the mass of the body having its initial velocity u. Let m is the mass of the body having its initial velocity u. M is the mass of the body having its initial velocity u. When a constant force exerted onto it, when a constant force F exerted onto it, it gains an acceleration. It gains a uniform acceleration A. It gains a uniform acceleration A. It gains a uniform acceleration A. And traveled a distance S. The final velocity acquired is v. The final velocity acquired is v.
And traveled the distance.
S. And the final velocity acquired is v. Then work done for this displacement. Then work done for this displacement.
And sir,
Work done
final
for this
displacement.
displacement. W is equal to Fs cos theta. Work done for this displacement. W is equal to Fs cos theta. Theta is equal to 0, cos 0 is equal to 1. Theta is equal to 0, cos 0 is equal to 1. Then W is equal to F into S. Here F is equal to MA. And V squared is equal to U squared plus 2AS. And V squared minus U squared is equal to 2AS. S is equal to V squared minus U squared by 2A. Substitute. Now W is equal to F into S. F is MA, S is this value, substituting, then finally you get here. Is that over?
Yes, sir.
Next heading, work energy theorem for constant force. Work energy theorem, very, very, very important. Work energy theorem for constant force.
So work energy and
Work energy theorem for constant force. Work energy theorem for constant force. Work energy theorem of constant force. Listen, same thing. That means whenever we do a work, there is a change in energy occurred. That change in energy can be in the form of kinetic energy or in the form of potential energy, or if it's an inclined plane, if you roll a body, its potential energy will change, kinetic energy will change. So it can be sum of change in potential energy plus change in kinetic energy. Anyway, you can accept it. But in your books and all statement, if you're asked state work energy theorem, means the statement you can give this way, very simple manner. Work energy theorem states that the change in kinetic energy of an object is a measure of work done over it. How much work you're doing an object, that can be easily measured by change in kinetic energy. Or in other words, if you can measure change in kinetic energy of an object, that is nothing but work done over it. But this is applicable to potential energy also. Remember that. Okay. So right, statement. Work energy theorem states that the change in kinetic energy of an object. Work energy theorem states that the change in kinetic energy of an object. Work energy theorem states that the change in kinetic energy of an object is a measure of work done over it. Is a measure of work done over it.
Sir, can you repeat the change?
Work energy theorem states that the change in kinetic energy of an object is a measure of work done over it. Is the measure of work done over it. Okay, now what you have to do, same way, same introduction, it will repeat, but until here. Look here, change in kinetic energy is equal to work done, measure of work done over it. So this derivation you will repeat until this reaches here. Okay, this is a proof for work energy theorem. Any doubt?
So do we have to write again?
If you want to write again, otherwise you write. Who is roll number 32? Sulaiman Ahmad. Sulaiman Ahmad, please unmute your mic. Sulaiman Ahmad states that the change in kinetic energy of an object is a force, is the measure of work done over it. So again, same thing you have to write, otherwise you write derivation same as before and write up to here. Like that you can write. If you want, you write again. But examination, it must be complete. You should not write derivation same as expression of kinetic energy. You should not say like that. Clear?
Yes, sir.
You should write completely. Can I go to next one?
Yes, sir.
Yes, sir.
Yes, sir.
Now, according to work energy theorem, we understood work is equal to half mv squared minus half mu squared. This is the measure of change in kinetic energy. That is the work done. But if it's a variable force, how will you approach? For variable force, we know the work done is directly is equal to integral, isn't it? x1 to x2
Yes,
f
sir.
dx. This is the work done, isn't it? In a variable force.
Yes, sir.
And this is equal to initial kinetic, final kinetic energy minus initial kinetic energy.
Initial kinetic energy.
Like this we have to prove. Okay, but this is not that important, but still there's a chance of asking. Let us go with this
Okay, sir.
derivation now. Work energy theorem with variable force. Work energy theorem with variable force.
Sir, the derivation, nothing addition is there in that derivation.
No, complete up to there. I told you, half mv square
Yes.
minus half. Next one, we are going to prove work energy theorem for variable force. Work energy theorem for variable force.
Sir, we'll do it using the integral method.
Integral method. Look here now. We know, right? You also write. We know kinetic energy. We know kinetic energy EK is equal to half mv squared. We know kinetic energy EK is equal to half mv squared. d by dt of EK, rate of change of kinetic energy is equal to half m into d by dt of v squared. Now let us have differentiation. d by dt of v squared is nothing but 2v into dv by dt. Actually, look here, we know this formula, d by dt of t squared. What is that? 2t, isn't it?
Yes, sir.
Yes, sir.
But again, actually, it is not complete here. Here you have to go with dt by dt again. T again you have to differentiate. But power 1. So when is the power 1, that 1 into t to the power 0 will go 1. That's what this part we are not marking here. Actually, that derivation is there. This part also we have to do. Similarly, look, d by dt of t cubed. We know 3t squared. But this t, again, we have to differentiate d by dt of t. But this is 1, d by dt of t. Because power 1. 1 t, okay, t to the power 0 will come. So it is 1. But in this case, look, v squared is 2v. But dv by dt is not 1. dv by dt is acceleration. Is it clear?
Yes, sir.
In normal differentiation, we know d by dx of x to the power n. That is nx n minus 1. You know that, isn't it?
Yes.
Similarly, d by dt of t squared is equal to 2t. But this t, again, we have to differentiate d by t of t. Power 1. 1t, 1 minus 1, 0. T to the power 0, 1. That's what this part we are not mentioning here. But here, look, same way. d by dt of v squared is 2v. V is again, we are differentiating d by dt of v. That is acceleration, that is not 1. Remember that, okay? So here I am writing d by dt of ek is equal to half m into, this is 2v into dv by dt. Then d by dt of ek is equal to half m, okay? This two cancel, so no half. So here m, v, dv by dt is acceleration. Then d by dt of ek is equal to m into, okay, v. This dv is what? This is dv by dt again, right?
Yes, sir.
1 minute. Here m into a, force, because we have to prove f dx, right? F dx. So m into a is f. So this is v. Then again d by dt of ek is equal to f into v is dx by dt. This dt, this two will cancel. Differentials will cancel. Then dek is equal to f dx. This is what we need. Now, if you integrate on both sides, dek we are integrating from ek1 initial to final ek2. Okay. That is dek is equal to integral f dx x1 to x2. This, if you are integrating, you will get ek. Dek, if you are integrating, total kinetic energy is ek. Its limits are ek1 to ek2. This is integral f dx x1 to x2. x1 to x2. And finally, this upper limit of ek is ek2 minus ek1 is equal to integral f dx x1 to x2. Okay. Right. This is the work done for variable force. But the first one is more important. It does not mean it will not come, you have to study. But first one, you should not ignore at any cost.
Sir, for exam, how many chapters are coming from physics?
For examination, work power energy full until work power energy from the beginning.
Okay, sir.
So still portion to complete. When I complete, I will tell.
6.
Sir, do we have to prove that dek equals integration?
What?
Do we
Again?
have to prove that dek equals in this integration?
No need.
No need, yeah.
Just you can write the same manner again.
Yeah.
Just a second, sir.
When you complete it.
Yes, sir.
Next one, law of conservation of energy. Law of conservation of energy. This already studied. Right. Energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. In a conservative field. Every time it's not possible in a conservative field. But it can convert from one form to another form. But it can convert from one form to another form. Write down. Next, law of conservation of energy in the case of an oscillating spring. Law of conservation of energy in the case of oscillating spring. Law of conservation of energy in the case of oscillating spring. Look here. Draw the diagram. First spring at the point A. This already we have done before also. At the point A. Then spring we are stretching. To the point B. This point it is x naught. This is 0. X is equal to 0. X is equal to x naught. When the spring is released, it will go to opposite side, same distance and compressed. This will get compressed here. This is C. Here also x is equal to x naught. This much point. Okay. So here EP is equal to half k, y is equal to x is equal to 0 here. Therefore EP is equal to 0. But EK is equal to half k x naught squared. This is my main point. Here EP is equal to half half k x naught squared. But here ek is equal to, we know the formula half k x naught squared minus x squared. X is equal to x naught. Therefore, ek is equal to 0. Here also ek is equal to half k x naught squared minus x squared. X is equal to x naught and ek is equal to 0.
So x is velocity, right?
X is maximum displacement.
Sir, what is EP in the C?
0.
Potential energy.
Potential energy maximum. Here EP is equal to maximum. EP is equal to half k into x naught squared. Same like this. Okay. So now we have to write one by one. Let us consider a spring oscillating. Let us consider spring oscillating. Let us consider a spring oscillating between B and C. Let us consider a spring oscillating between B and C with respect to mean position A. Let us consider a spring oscillating between B and C with respect to mean position A. Then write at A, x is equal to 0 and EP is equal to, write this, whatever it is, see, same thing. Half k into 0 is equal to 0. EK is equal to half k x naught squared. The total energy ET is equal to EP plus EK. That is half k x naught squared plus 0. That is equal to half k x naught squared. At B, x is equal to x naught. Then EP is equal to half k x naught squared. EK is equal to 0 and E total is equal to EP plus EK. E total is equal to half k x naught squared. At C, same thing. EP is equal to half k x naught squared. EK is equal to 0. EK is equal to 0. Then E total is half k x naught squared. The expressions 1, 2, and 3 shows that at A, B, and C, during its oscillation, total energy remains constant.
So what was the last sentence, sir?
The expressions 1, 2, and 3 shows that the expressions 1, 2, and 3 shows that expressions 1, 2, and 3 shows that the total energy during the oscillation remains constant. This proves laws of conservation of energy. This proves laws of conservation of energy.
That total
Expression 1, 2, 3.
energy,
Shows the total energy during the oscillation of the spring remains constant. This proves laws of conservation of energy.